What I'm going to talk about today is a way through which your computers that you are using today can work faster at lower power. That's basically the message of what I'm going to do. And the talk has two parts. One is theory and one is practice. I was asked to do a 45-minute theory and 45-minute practice. I think the theory part is longer. The practice part is shorter because I don't expect anybody here in the audience to be versed in electronics. So I'm just going to do the practice part a little less, which is also great for me because I don't know anything about it. All right, so what's the problem we're dealing with? It's a communication problem. You have two chips. These can be two chips in your laptops, in your phones. One could be a CPU, one could be memory, or any other two chips. And you want to, these chips are connected using electrical wires. And you want to transmit information from chip 1 to chip 2 reliably. So it's very clear. It has many, many applications, obviously, because all the electronic devices that you have chips inside of them, and those chips need to be able to talk to one another. The issue is that the speeds are increasing. So if you believe what EMC postulated a few years ago, the amount of data doubles every 18 months. And that data has to be somehow processed by these chips. So you can say that, on average, the amount of data that goes in and out of a chip doubles every 18 months. On the other hand, the real estate doesn't double. The pins you have on your chips, you don't have more pins. So you have to send data at higher and higher rates through the existing wires. And as we will see, this causes issues because the higher the frequency of the operation, the more noise you have. And that noise you have to somehow cancel. And the canceling costs power. So how do we do that? So usually when we talk about this, we have to talk about the channel, the communication channel. So as I mentioned, there is noise when you transmit data between the two chips. And if you know, it's actually a very good thing if you don't know anything about communication channels. If you know some things about communication channels, you may be inclined to think of this channel as something you know, DSL, for example, or wireless, or maybe a magnetic hard drive. And the point is, the channel that we're dealing with here is none of the above. There is, in all these channels, noise is dominated by what's called random noise. You don't know really anything about the nature of that noise. In fact, on this channel, the noise is mostly deterministic. Mostly you know what will happen, but you can't really do anything about it because you're extremely limited on resources. Now, we are in a theoretical computer science setting here, and I'm sure a lot of you have heard about randomness. And you know that randomness in itself doesn't really exist. You have to say something, the randomness is always with reference to some computational model. The more handicapped you are, the more things look random, right? Here is the same thing. You're handicapped. You're very limited on resources. So even if the noise is deterministic, you have to think of it as random. So often when I give this talk, it's in front of people who know something maybe about wireless or information theory. And so there is something I call the rule of thousands. If you work in wireless, then the throughputs you're dealing with are typically in the megabits per second, maybe hundreds of megabits per second, but still megabits per second. When you do chip-to-chip communication, it's 1,000 times higher. We're talking about gigabits per second. The energy per bit that you use when you're dealing with wireless is typically measured in nanojoule per bit, so 10 to the negative 9 joule per bit. In chip-to-chip, it's measured in picojoule per bit, so 1,000 times less. And the time you have to recover a bit in wireless is measured in nanoseconds, and here it's measured in picoseconds. So you have less energy at your disposal, and you have less time at the same time to detect a bit. 1,000 times less. All right. So to make matters worse, there are many, many different noise types you see in chip-to-chip communication. And I'm just going to talk about it. Don't even bother reading, maybe. When you have an electronic device, a chip, and you are sending data, you have a voltage that feeds the wires. But this voltage is fluctuating. Sometimes if you send a 1, then you're pulling from your source, and if you send a 0, you're not. So this, depending on the pattern of what you're sending, this source may be fluctuating, and this is called the simultaneous switching output noise. There is a reference noise if you refer, usually when you send data, it's a voltage, right? So if you send a voltage on the wire. And if you want to see whether you send a 1 or a 0, you need a reference to see whether what you receive is above something or below something. And that reference may be different when you send the bits versus when you receive them. That's called reference noise. Crosstalk. This is a really tough one. If you have wires that are close by, what you do on one wire will cause the other wires to behave in a really erratic way. Electromagnetic interference, that right? I don't think I've seen it recently, but often when you have a phone in front of a loudspeaker, then you hear this tick, 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 electromagnetic interference. Common mode noise. Again, if you have a power source and you're feeding all the wires, that source may fluctuate. So all the values on the wires may go up or down at the same time. By far the worst type is called intersignal interference, and I'll talk about it a bit later. And then there is something called thermal noise, which is Gaussian noise. Actually, Gaussian noise in these systems is minuscule. And noise is really completely dominated by the other one. So this is, maybe a qualitative or quantitative view of what the various noise types, how much they contribute. And don't even, I can see that you can't read the text, but that's not really the point. The point is that practically all of the noise is deterministic. So in other words, if you know what data pattern you're sending, you could somehow mitigate crosstalk, you could somehow mitigate simultaneous switching output noise, and so on and so on. And there's just a very thin slice that's dedicated to this Gaussian noise. Again, resources are tight, so you can't really do anything. So, as you probably know, I started a company called CanDoBus that tries to commercialize the techniques that I'm going to describe here. And since then, I am in absolute awe of what engineers have achieved. For all I know, none of these devices should work. It's absolutely impossible. It's absolutely impossible. I mean, the kind of problems they solve on a daily basis, it's mind-boggling, especially analog design at high speed. It just should not work, but it does work. So how does it work? Because these noise types, they are often dealt with using many different techniques. For example, the simultaneous switching output noise is either through the modulation, what you're sending, or the design. Reference noise, again, modulation or the design of your system. Crosstalk is how you lay out your wires, and again, the design of your system. Electromagnetic interference, well, if you can't control it, you shield everything. Shield the hell out of your signals. Put a huge LED. I mean, of course, you can't do that on a small device, but you could potentially do that, and so on and so on. And so what I'm going to talk about today are all those noise types where modulation plays a big role. And I will introduce to you a new modulation scheme that practically takes care of, well, it doesn't take care of these, but is a modulation scheme that is versatile enough to be resilient to all of these noise types. Yes, please.
Just wondering if there's some trade-off issue with different kinds of noise. Like if you decrease one noise, it will cause another type.
That's a very good question. The question is whether there is a trade-off between the noise. Yes, it is. You could, for example, increase the voltage. And with increasing the voltage, you could mitigate the reference noise. But then increasing the voltage, unfortunately, also increases crosstalk noise. So you need something that kind of simultaneously takes care of all these things at the same time. So what do people do today? As I mentioned, basically, bits are transmitted by voltage levels on the wires. And in high-speed signaling, which is basically what you're using in your devices today, what you do is you take a high voltage and you think of it as a 1, and a low voltage, you think of it as a 0. And there is some it's called the common mode voltage, something in between, which you can think of as 0, right? So it could be that the high voltage is 450 millivolt, the low voltage is 350 millivolt, and the common ground, or the common mode, is 400 millivolt. Anything above is 1, anything below is 0. It's called non-return to 0 signaling, which means that there used to be something that was return to 0 signaling, which means you go up, and then you go to the middle, and then you go down or up again. In high speed, it's impossible to use that. So I'm trying to explain this sort of mathematically, what happens. This is what is called a single-ended driver. So you send bits, you modulate the bits now as plus or minus 1, depending on whether they are above the common mode voltage or below. And when you detect, you have a reference voltage, which is kind of the middle. And basically, what you detect is the sign of the received value minus the reference voltage. Right? That's how you would do the detection. So here is a way I would like for you to think about it. So you're sending plus 1 or negative 1. You have a distinguisher, which is kind of the 0. And when you're transmitting these symbols, because of noise, they start moving. And sometimes they move below or beyond, sort of beyond the distinguisher. And at that point, you think of it as noise. It's kind of clear. So, you can start sort of looking at this. And it turns out that single-ended signaling is actually very good for low speed. For high speed, so maybe I should also tell you what high and low speed mean. Today, when we're talking about high speed, we're talking about data that's being transferred at above 20 gigahertz. So 20 gigahertz or 20 gigabit per second per wire, right? And low speed is maybe below 1 gigabit per second. So you might ask what happens between 1 and 20. Well, it depends, right? So anything above 20 is high, anything 1 or below is low. So single-ended is perhaps good for low-speed signaling. And it's not bad in terms of intersimilar interference, but practically it sucks in any other dimension. That's what made people look at something else called differential signaling. In differential signaling, you send one bit across 2 wires. And how do you do that? You send complementary bits on the wire. So if your bit is a plus 1, you send a plus 1 on the top wire and a negative 1 at the bottom wire, and vice versa. And then when you want to detect the signal, you take the difference of the top wire and the bottom wire, and you take the sign. All right? So we lost something here, meaning we are sending half a bit per wire. But we gained actually quite a bit. And that's the reason why in all the devices you have, everybody is using differential signaling. Everybody. It's the bread and butter of high-speed electronics. So what happened here is that you don't have a reference anymore. Right? That's pretty cool. Just completely disappeared. So there is no reference noise. It has also very good advantages in terms of electromagnetic interference and a bunch of other things. So it's pretty good in terms of the other noise types. But in terms of intersimilar interference, it's perhaps not as good as single-end signaling. And I realize I didn't tell you what intersimilar interference is, but bear with me. So remember that until I actually tell you what it is. Yes, please? That's one of the... Yes, it's one of the consequences, but it's not the only one.
What do you do when there is a zero?
When what?
When there is, when B and minus B, like one of them sends a 1, one of them sends a, like instead of saying sending 1, instead
Yeah, well, you know, if it gets wrong, then it's basically random at that point.
Yeah, so how does the system do it? It just ignores that?
It completely depends on how you implement it. You know, so the question was, what if at the comparator you get something that's close to 0? What does the comparator give back to you? And it completely depends on the implementation of that comparator. Very often, if it's, so all these comparators have a blind gap, or a blind, what do you call it, region. If you are within that region, then the output is basically random. So the design process makes sure that you never, ever get there. That's one of the things that these engineers do. Yes, please.
Comparing of the two lines, do we consider that the noise, the conditions that induce noise, are similar in both of the lines or different?
That's a good question. So the question is, I guess, with the lines or with the columns?
With the lines.
Well, you know, it turns out that all of these noise types depend on the frequency of the operation. So within a column, I have the same frequency, so the conditions of noise are more or less the same. At least within the rows in a column. In two different columns, the frequencies are different, so the noises are different. So for example, when you use differential, you have to go at twice the frequency to get the same throughput per wire. So that's why the intersignal interference is worse. Yes, please.
You talk about single-ended being good for low-speed communication. Why do you want things that are good for low-speed communication? Can't you use the high-speed things in a low-speed?
Sure, you can do that, but then you have too many wires. So low-speed communication, think of it as a parallel line. You remember, I don't know how old you are, but when I do remember these thick wires connecting printers to, remember them? So these are single-ended. If you use differential, then the wires would be twice as thick. Okay, so are there other solutions? So, you know, the problem in this field is practically all the noise is what we call frequency selective. And it gets much, much worse with higher frequency. It doesn't go linearly or anything. It's almost exponential. So you want to reduce the frequency of the operation. But how? You know, one way that immediately people can think of is, what if I send more levels per wire? Right? I mean, if I had 4 levels, for example, then I could send twice as much at the same frequency. If I had 8 levels, then 3 times as much. No? Looks like free lunch. And unfortunately, the industry has gone in this direction, because they really have not really thought about the consequences of this. The point is, what happens to noise if you do that? It turns out, and I'm just doing it for 4 levels, that some noise types are good, like EMI and common mode noise. Other noise types absolutely suck, like intersignal interference. And again, I have not told you what ISI is, but think of it as the major contributor of power when you want to detect the signals. The other option is to generalize differential signaling. Differential signaling, you pull 2 wires together. What if I pull more than 2 wires together? Can I send more data per wire if I do that? And what happens to noise? And that's what we call chord signaling. It turns out that chord signaling is a simultaneous generalization of practically all other modulation schemes for sending data between 2 chips. So what's the theory? And I'm not going to give you a full theory here, because unfortunately I have to kind of develop everything. But at the end, you actually see a definition. So that's a good thing. I'm not going to talk about constructions of these codes or test chips or any of the electronics, even in the second part. So let me tell you how we think of this. If you have 2 independent wires running single-ended signaling, then of course the set of signals that you're sending is all 2-dimensional vectors with plus or minus 1 as components. So the way we think of this is we think of them as points in a two-dimensional space. And we think of the comparators as hyperplanes in this space. So if you look at one comparator, it's just a line on 0. It's a distinguisher. The distinguisher can distinguish 2 points that are on the opposite sides of that line. But of course, it cannot distinguish 2 points that are on the same side of the line. So in order to be able to distinguish them, we add another distinguisher. That's the second comparator. And with that, of course, all the points are distinguishable. So I take basically the R2 and I subdivide it into 4 chambers. And in each of the chambers, I have one of the values that I'm sending simultaneously on the 2 wires. And of course, all of this is quite simple. And if you have n wires, you can think of it the same way. You have points in the n-dimensional space, and the comparators are just hyperplanes that are separating the points. You need to make sure that when you look at this hyperplane arrangement, so each hyperplane is central, goes through 0, it gives you an arrangement, that every chamber of this arrangement has at most one code word in it. So here is one example. You want to send 2 bits on 3 wires. You could, for example, have 8 points on a regular octagon. And the distinguishers are just the lines that go between these points. And if you really want to implement it, it turns out it's better to kind of shift it a bit. And the distinguishers become very simple. These are x negative y, x plus y, and just y. Meaning that if you look at the 2 values, you take the sign of the difference between the 2 values, the sign of the sum of the 2 values, and the sign of the second value. And with these 3, you can distinguish the 3 bits. So every one of these chambers is, of course, given by a sign signature. Then if you go to 3 wires, you go into the 3-dimensional space, and so on and so on. So the general architecture of this signaling is the following. You have, yes? The only restriction, no, central. They're central. They have to go through 0. They're not affine. They can be anything. Of course, in implementation, no. If one of your hyperplanes has square root of 2 in it, and it's it's fragile, so if you don't have square root of 2, everything breaks down, then you can't do it. Yes. There's some small restrictions, but these are implementation restrictions. So, you get the bits, you encode them, and encoding means you map the bits to the code words you send on the wires, and then you have these comparators, and out of the comparators come other bits, and from those other bits, you recover the original bits. So what are the parameters? You have the interface size, the number of wires, little n. You have the number of comparators, which I call C. And then the first question that you might ask is, if I have C comparators in the n-dimensional space, what's the maximum number of chambers I can get in the hyperplane arrangement? What's the maximum number of code words? And interestingly enough, this was solved by Zaslavsky in the 1970s. That's the number. That's the maximum number of chambers that a hyperplane arrangement with C hyperplanes in the n-dimensional space can have. So you can tabulate the numbers, and then you can, for example, see that you will be able to transmit 7 bits on 4 wires using, what is it here? 8 comparators. Could have also. But then the question is, what happens to noise in these settings? If you apply this up to this point, chord signaling will be much worse than any other signaling type. At least, chord signaling, or the other signaling types are, of course, special cases of chord signaling. But you need to do a lot more to get something that's useful. You really need to look at the noise and design the hyperplane arrangement and the code words in such a way that you have resilience to noise. And I will give you some example. This is a case of a mobile memory. And I do realize that you may not know these, what is called eye diagrams. But think of it this way. So these are waveforms that you're sending over the wires. And then they're received at some point. And think of it this way. The bigger the blue part, the more resilient the system is to noise. If you sample the signals within the blue part, you're OK. Outside of the blue part is hell. OK, so if you use single-ended signaling, it turns out that the blue part has a certain width, 36 picoseconds, and a certain height, 27 millivolts. If you use the hexagon, so using the hexagon means you're sending more bits per wire, so you have reduced the frequency. So you can think of, oh, frequency is reduced, so noise is better. It turns out you actually lose. The width becomes smaller, and even the height becomes smaller. If you go and look at the octagon, it's even worse. Well, here the width went up a bit, but the height dropped. So here are some examples. So what you see in green is the width of these eyes. What you see in yellow is the height of these eyes. Sorry, what you see in blue is the height of these eyes. What you see in yellow is some kind of some kind of performance number, so I'm not going to get into. And you see, as you decrease the frequency, you're actually losing. So what's happening? What is happening is that if you have more and more code words, the chambers are becoming smaller and smaller. And if the chambers are smaller, then it doesn't take you much to take a point that was in some chamber and push it into some other chamber. And that's because you have not taken care of the noise. What we just did was we just put these points into this n-dimensional space. We didn't ever say anything about how we have to put these points and the hyperplanes in order to be resilient to noise. Of course, right? So this is the system that we've designed, and what you see on the right is what we are actually licensing to our customers. And it's a lot better. It's a lot better. So how did we design it? And for that, finally, I have to talk about something called intersymbol interference. So what is intersymbol interference? Does anybody here know about it? Have you seen it? Yeah, some people may. But I guess in computer science, you don't really see these things. But here's the thing. So these are rectangular waveforms you're sending on the wires. You have put a lot of effort into making these almost rectangular. Everything is great. But the problem is that when you transmit that over these wires, there's something called, the channel, what it does is it takes the energy of your signal and pushes it into the signals that follow later. There is an inertia on the channel. So the perfectly rectangular shapeform that you sent in the first instance becomes this blue curve, and the second one becomes this red curve, and so on and so on. And now if you look at one particular point in time in which you want to send to sample something that's supposedly negative, because of what is still remaining on these wires, these things get added. And once they get added, you have a certain period in which something that was supposed to be negative becomes positive, and you make a mistake. This is a very normal thing in practically any communication channel. The geometric interpretation is the following. Suppose that you're sending the code word that's the small blue circle, and that in the previous round you sent the bigger blue circle. The blue circle, the energy of that signal is still present at least part of it, is still present on the wire, and that pushes this blue signal over this boundary line of the chamber, and you make a mistake. And now comes really the main parameter that is really so important in this. And this parameter is due to, I guess, a friend of ours, Ali Hormati, who you probably know, who is one of the engineers working for us. We call it the ISI-Ratio. If you know coding theory or algebraic coding theory, you know that there is a dimension, there's a block length, and there's a third parameter. Anybody knows that? It's called the minimum distance. Without the minimum distance, you're just doing linear algebra. With minimum distance, it becomes much more complicated. And this is very similar here. We call it the ISI-Ratio. The ISI-Ratio is a figure of merit that describes how well one of these comparators performs. So for every one of the comparators, what you do is you take the distance of the closest point to the comparator versus the distance of the furthest point from the comparator. And the value of that furthest point, the distance of the furthest point, divided by the distance of the closest point, is called the ISI-Ratio of that comparator. The larger this ISI-Ratio is, the worse this comparator performs, because there is some point that's very far and some point that is very close, and that point that's very far pushes the point that's very close over the comparator. Now, once we found the ISI-Ratio, we started experimenting. And indeed, you can have codes that operate in completely different dimensions. If they have the same ISI-Ratio and you're sending the data at the same frequency, you will see roughly the same horizontal width of this blue region of these eyes. And if the ISI-Ratio is large, never mind that the one on the right looks like lots of big blue eyes. This is actually a closed eye, so it doesn't matter how it's represented here. But if the ISI-Ratio, by the way, the ISI-Ratio doesn't need to be an integer. It doesn't even need to be rational. You see, in this case, the ISI-Ratio is irrational. If the ISI-Ratio is large, you lose. So if you design your code in such a way that the ISI-Ratio is small for all the comparators, you're good to go, at least in terms of ISI. What about the other noise types? There is one elegant construction that takes care of all of them. For example, if you look at common mode noise, what common mode noise does is it adds values simultaneously, the same value, to all the wire values. That's common mode. It's really bad for signal integrity. It's really super bad for signal integrity. And so you can think of it the following way. So if you look at it sort of in this setting, the comparators should evaluate to 0 if you send the old 1 vector. Comparators are linear functions. If you apply the linear function on the new values, and the value of the linear function is 0 on the old 1 vector, then the x's here, they all disappear. And all the code words should be kind of orthogonal to this all 1 vector. These are the two things you want to have. And so for differential signaling, that's exactly what happens. The code words are +1, -1, and -1, +1. And the common mode direction is the direction that's orthogonal to the line that connects these two code words. So what is happening here is you start with a single-ended signaling, and there is an orthogonal transformation that you just saw that, right? This was this transformation that just rotated the constellation. And what happens is, what we found is that this is a general thing. So whenever you have a signal constellation, points in a plane and hyperplanes, you can transform it using an orthogonal transformation and make it common mode resistant. That's this elegant construction that can take care of everything. And the way it works is you need an orthogonal matrix. And by orthogonal matrix, I mean really matrix in which just the rows are orthogonal pairwise. And the matrix should have the form that if you add all the columns, you have everywhere 0 except in one position, for example, in the first position. Then you can take the original code and make from the original code one that's common mode resistant in a very simple way. We call it the tempering process. So in 4 dimensions, for example, my favorite orthogonal matrix is the Hadamard matrix. And you can use that in order to get a signaling scheme that transmits 3 bits on 4 wires instead of what you would have with differential, which is 2 bits on 4 wires. You know, it looks like going from 2 to 3 is really not a big deal, but it's a huge deal in these devices. And we are very hopeful that this scheme will be in your devices that you're working with today in a few years. Yes, please.
When you do this, does it mean more energy output from the system? Or does it, will our phones start burning up?
Yeah, nobody would buy a system where you send more. Actually, what happens is less. So the power of this, the total power for the transmitter and the receiver, is less than what you would do with differential signaling. And, you know, because the frequency of the operation is lower.
I'm just saying that from like a philosophical point of view, there's no free lunches, so what are we losing here?
The only place where you lose is what's called the vertical opening. So the vertical opening is smaller than, it's difficult to explain. So let's put it this way. If you had equal throughput over the 4 wires, then still the vertical opening here is better than what you would have with differential signaling. If you have equal frequency, which means differential signaling has 2/3 of the throughput of here, then the vertical opening is smaller than what you would have with differential signaling. But we're talking about equal throughput because you want to increase throughput. So this is a scheme in which you can send data at a lower operating frequency. You lose a little bit in terms of the vertical opening, but you can compensate for it with very little power. And so you're good to go. And as I said, I'm hoping that this will be in all your devices in a few years. Yes? The wire length is an issue. It's called skew. Absolutely. So that's a very good question. The question is, if you have many wires, and if they are not completely matched, does that cause a problem? It absolutely causes a problem. Especially at very high speeds, you want the wires to be matched almost perfectly. So the question is, if they are not matched, what do you do? And we have algorithms for matching the signals. That's where you need algorithms. Sorry? You have to tune it, but if you think about, for example, if you're running things over a cable, you can't tune it immediately, one time, because people tend to bend the cables. But the point is, if you are operating, for example, at something like 40 gigahertz, which means 25 picoseconds for every bit, we assume that the bending of these signals is maybe 10 times slower, which in reality it's a lot more than 10 times slower, right? Because how can you bend things at 40 gigahertz? It's just not possible. Human. But this is how our algorithms work. Okay, so also the common mode noise disappears by construction because we have central hyperplanes. It turns out that there is no reference noise, by the way, because of the centrality of the hyperplanes. There is no EMI is something I will talk about in a minute. And also SSO disappears, and I didn't talk about it really. But in general, by using this kind of construction, you have out of a sudden a coding scheme that is resilient to all the noise types by design from the start. And that's a good thing. All right, so if you want to see a definition, here is the definition. Okay, so what we call a chordal code, it has 4 parameters. Little n, number of wires. Capital N, number of code words. little c, number of comparators, and I, which is the ISI ratio. So this code has two components. One is the code words, one is the comparators. The code words are C, comparators are lambda. So you have little c comparators, and you have capital N code words. So the distinguishability says that for any two code words, there is some comparator such that the two code words are on opposite sides of that comparator. And the ISI tolerance says that the ratio between the furthest point from a comparator and the closest point is never bigger than I. So, of course, there are lots of practical concerns that have been swept under the rug, but this is it's a good enough definition to start working with. So the fundamental question is, if you have little n and capital N, find the minimum ISI ratio I such that there exists such a code. The number of comparators from the start is perhaps not so important. Eventually it becomes important. Yes?
What if you somehow do the differential? So the image that I have in my mind is this of the 8 points.
The octagon.
And then the separated by hyperplane.
Mm-hmm.
So wouldn't it make sense to try to make these points just make that the radius bigger somehow? Or is that like by doing the differential? Wouldn't that also make it?
So maybe if I understand correctly is if the points were what we call a spherical code. So you are on a sphere and you try to maximize the distance between the points.
Yeah, just increase the radius.
Yeah. Well, the radius you can't just increase because that means power. You're within a radius of 1. But you could try to have on the unit sphere, you could try to have points that are as far as possible separate, which is called a spherical code. And it's very tempting to think that these are the same objects. They're not. There are spherical codes that are really good in terms of spherical codes, but absolutely miserable in terms of chordal codes, and vice versa. There's some connection, but only some. All right. And the rate of this code is the log base 2 of the number of code words divided by the number of wires, or what you call pin efficiency. Okay, so some trivial bounds. The number of comparators actually, this is a wrong bound. The number of comparators is at least the log base 2 of capital N. Because every comparator gives you 1 bit of information at most. The ISI ratio is never smaller than 1. It's the ratio between the furthest point and the closest point. This cannot be smaller than 1. And the number of code words is upper bounded by Zaslavsky's formula. So here is a concrete question. What is the best ISI ratio you can find in dimension 3 and 16 code words? So I've developed combinatorial optimization schemes for this kind of problems. And what I found, the best thing I found was 2.39304, 11 comparators. It's absolutely impractical. We would never use such a thing in any of our products. But it's an interesting question, nevertheless. I don't know the answer to this question. But I have a conjecture. Yes, please? I'm sorry?
That's not the solution.
I don't think at all that this is a solution. I have a conjecture that says that the number of code words is less than or equal to 1 plus the ISI ratio to the power of n. And if the ISI ratio is 1, I know how to get that. But in general, I don't have a solution to this. Just very quickly on the electromagnetic interference. If you have 2 wires, you have something called a charge loop. So you put these wires together. At some point, they come together and make a rectangle. If you have a rectangle and you have a sinusoidal wave that's going through this rectangle, then this rectangle here creates something that's called an electromagnetic far field. And the strength of that far field is proportional to the square of the frequency times the I. Now, this I is different from the other I. This is the charge, or you see, I'm not the current exact. I'm not an electrical engineer. Times the area of that rectangle. So I'm assuming that all these parameters are 1, so that the figure of merit is 1 for when I want to measure the electromagnetic interference. If you look at differential signaling, you have two different signals, +1, -1, and -1, +1. And the average strength of this, and if you have equal probability on these, the average strength is 1. If you have two differential lanes, then this is the kind of things you have. +1, -1, +1, -1, etc. In some cases, they cancel. In some cases, they become larger. But the average strength is still 1. So what do you do if you have one of these chordal codes? So you have the C0, C1, C2, etc. running on the wires. I look at it as different rectangles. And I just do a little bit of adjusting. So I put values on these edges of these rectangles so that the sum of the values is exactly what you want to have. And if I do that, it turns out that on average, this is what I get. So if the values you put on the wires is C1, C2, C3, etc., on average, the value of the figure of merit for the far field is this number over there. Which is, if you look at this C as a polynomial, it's the derivative of this polynomial at 1. And if I send the code words equiprobably, then this is the average, the figure of merit for the average far field. Now, one of the things that our customers always ask us is, besides what you asked, what if my cell phone starts burning? And we convince them the power is actually small. The other thing they ask us, they are so this differential signaling is so ingrained in their heads that they think there is nothing else that can give you a smaller far field. And if you look at ENRZ, which sends 3 bits over 4 wires, it turns out the strength, the figure of merit for ENRZ is larger. It's 4 over 3, rather than 2 differential lanes, which is 1. But keep in mind, for equal throughput, the differential has to run at 1.5 times the frequency. And the far field is proportional to the square of that. So the figure of merit for differential is actually 2.25. And for ENRZ is 1.33. And up at this point, nobody believes us. So it says that ENRZ is actually better in terms of, and you can then run an experiment. Interestingly, they believe experiments, but they don't believe the math behind it. So what you see here is the strength of the far field of the two signaling schemes over a frequency range. And by the way, on the vertical axis, we are looking at the logarithmic scale. So if something is much smaller here, in reality, it's a hell of a lot smaller. OK, so here's a summary of the theory part. I didn't talk about all the constructions that you can have and so on. But it does provide you a mathematical framework, a concrete framework for the design of coding schemes across multiple wires. If you look at it theoretically, you want to find the best ISI ratio for a given number of wires and a given number of code words. And if you look at ISI ratio 1, there is an optimal class. And the optimal class is really the hypercube. Now, the definition of this chordal codes, I didn't give you really the full definition because that's more complicated. But you can extend it in various ways in order to be able to gain maybe a little bit more out of that. Okay, so maybe it's a good time to take a small break. And the application side is actually quite short. So, yes, please. Very good question. I'm waiting for that question. They suck. They cannot work here. So the question was, can you just use an error correcting code instead of this? Oh, no, it wasn't a question. That's a question I wanted to answer, but okay. Yes, please.
I mean, if you have error correcting code in your coding, I think that's the Chordal method of
I see.
that means, if you incorporate error correcting code into it, does it matter at all?
So I don't know how to incorporate it into the definition of the code. The Chordal code is analog. It used analog signals. The error correcting code used digital ones. But you can have an error correcting code at the beginning and at the so before the bits go in, you encode them, and after they come out, you decode them. And that's what some people do, which is a good thing. The problem is, so maybe now I answer the question I wanted to answer, which is, couldn't you do all of this by designing an error correcting code? The answer is no. And, well, at least I don't know how to do it. And I know a little bit about coding theory. So the issue is, there are many issues, in fact. One of them is the noise type. The noise is very different from what you find in normal error correcting codes. That's number one. Number two is, generally when you use error correcting codes, for the kind of noise that you hear, you need to have long codes. And long codes mean delay. In chip-to-chip systems, the largest delay you can handle is maybe 1 or 2 nanoseconds. So you have to have really short codes to be able to deal with it. And also, I don't know of any code that can deal with the various types of errors you can see here. And the coding we are using is not really an error correcting code. It's really a modulation scheme, right? So you want to make the modulation scheme as resilient to noise as possible. And then you may want to use an outer code, which is digital. And we actually do that also in our systems. Because if you get a bit error rate of 1e minus 9, generally in systems you want 1e minus 20. So if we get 1e minus 9, then with a very lightweight code, we can bring it down to 1e minus 20. We could also do 1e minus 20 by design, but that means much more cost because you need to design these things, over-design your system. Yes, please.
My question is not a computer science question, but I'm just asking out of curiosity. Does this affect the form factor in any way?
Yeah, the question is whether it affects the form factor. The answer is yes, it becomes smaller. Yes, it becomes smaller. No, the wire count is still the same. I'm not using more wires. I take the same infrastructure as it was before. I just put different signals on the wires. And the reason it becomes smaller, that's actually another question that our customers ask. And they just don't believe the answer that I just gave. Because they think, because of this big complicated structure of chordal codes, you need a lot more processing. Yeah, the reason is, well, there are many reasons, but one of them is that you can share resources among the wires. By sharing them, you don't have as many components in your system. So the form factor, the physical form factor becomes smaller. Okay, applications. There are many applications, but in some way, I'm an information theorist, even though I actually never even took a course on information theory. And I can't really say I'm one, but still. Let's go back to Shannon. Has anybody gone to an information theory symposium? Probably, yeah. Last time I was there, I was in, where was it? In St. Petersburg. So I was, there's these parallel sessions. So I'm walking down the hall, and there's one parallel session on my right, another one on my left, and in every single room, I was hearing, as Shannon said, as Shannon did, as Shannon, and so on. It was really like walking through a church or something. So I don't want to be that person, okay? But still, of course, he had fundamental fundamental contributions. And one of his fundamental contributions was actually his master thesis, in which he introduced digital design. This was an abstraction that has enabled these systems. Because if everything was analog, it would have been very difficult. What he said is, give me a clean 0, give me a clean 1, and then I can synthesize any Boolean function you want. Which is, today we all know about it. Didn't exist before his master thesis. All right. So Bell Labs, of course. Anybody worked at Bell Labs beside me? Oh, we all did. Okay. At least the two of us did. Where were you? In which site? Okay. I was in this one, Murray Hill. So these are kind of. I'm sorry?
I was in 112.
Oh, you were in 112.
Yeah, but
I was in the place that's completely useless, which was mathematics of communication. Useless for the company. All right. Okay, so the other thing is, of course, the invention of the transistor. And you can say, whenever at Bell Labs, you just get this thing through osmosis, because it's just so much history, right? And these are the three. Well, actually, only two of them apparently invented it. The one in the middle put himself on the patent. But that's a different story. Okay. So, so Bell Labs invented transistors. And the reason they invented transistors were switching networks. They wanted to have more compact switching networks that used a lot less energy, because they knew that with the light bulbs, they will not be able to handle world telephone traffic. And it's actually one of the most interesting things. They didn't know that transistor existed, yet they put a team on it to invent it. Who would do that today? And time and money, well, time, they cared about time, of course, but somehow they didn't care about money. But one thing they didn't realize was integrated circuits. Because they thought they take these transistors and connect them with wires. And I think there is a famous quote that says, we can make systems up to 1,000 transistors, but no more. Too many wires, right? Integrated circuits was a completely different story, because now you have one piece of silicon, and everything is on it. And the companies that did that, Hewlett-Packard, Intel, etc., they won. Okay, so you may have heard of transistor sizing. Have you heard of size of? I guess you have heard of it. So from every generation to the next, you try to make the physical form factor of the transistor smaller, because through that, and by the way, they go down by a factor of 1 over square root of 2 in every, because through that, you can lower the power by a factor of 2, and you can increase the speed by a factor of 2. I'm not going to talk about this a lot, but you want to make these smaller and smaller. Do you know what the smallest form factors are today? Any guesses? 7? 6? Uh-huh. So the device you have, it's an iPhone, right? Which one is it? 8. So what do you think is the form factor in the transistors here? It's not 6, it's 16. But the one that Cisco and others are using now is 7. And there is design being done in 5, and 3 is going to be out the door, 3 nanometers. I mean, I'm not sure it will work, but that's what it is. Okay, so reducing the size of a transistor allows to pack more transistors into the same area. It decreases the voltage, and it increases the speed. And that's the free lunch you were talking about. Well, it's not completely free, because you have to actually make it. But so you know about Gordon Moore? Gordon Moore was one of the founders of Intel. And Gordon Moore goes back to Shockley, if I may just say one little thing about it. So Shockley, the middle inventor of the transistor, he had a very difficult character, apparently. So he said, I'm going to quit Bell Labs. I'm going out to California to start a silicon company. And the answer was, what? California? There's orange orchards. What are you going to do there? There's no silicon there. So he went there. I think his mother lived there, so he wanted to be close to his mother. And he's generally credited as the man who brought silicon to Silicon Valley. So he started a company called Shokrallahi Semiconductor Labs. And the one thing he did well was to recognize talent. So he hired these really young kids from Stanford to come and work for him. But he was a bit weird. So for example, one of the things he did was, at some point he was convinced that somebody in the company wanted to kill him. So one day, everybody comes in, he locks the doors, and he has a lie detector there. And he says, nobody leaves before going through the lie detector test. So these guys, really good guys, at some point they left, Moore being one of them, and went to they started a company called Fairchild Semiconductor, which still exists. And these are the guys who went to create Intel later, HP, Kleiner Perkins, if you know, venture capitalists, et cetera, et cetera. It's a very interesting story. But anyway, Gordon Moore, he wrote a paper called Cramming More Components into Integrated Circuits. And he came up with something that's called Moore's Law. He said that the number of components that you can pack into a given area grows exponentially with time. So the vertical axis is the log base 2 of number of components. The horizontal axis is time. And he actually had only very few data points. These are the circles there. And he extrapolated from there. And this is what has been driving the electronics industry for the last 50 years. Now, some of it is self-fulfilling prophecy. So the electronics industry tried to match this. Some of it is just his foresight. In fact, he had a lot of foresight. This is one of the cartoons in his paper. He says, at some point, electronics becomes so interesting and so popular that in a department store, people are just lining up to buy electronics gadgets rather than other things. And of course, we know that, right? The paper is, joke aside, it's a paper full of foresight. It's just an amazing paper. It's very, very easy read, maybe 7 or 8 pages, but definitely a must. It's a fantastic paper. So these are some of the numbers of transistors in the various devices that you may or may not use. So the reality, so Moore's law is what you see in green. The reality is what you see in blue. And the reality of our lives is that Moore's law does not hold anymore. It's dying. So if Moore's law is dying, how can we get better, faster, and lower power devices? How is this possible? What can happen there? In fact, Moore's law is really for digital circuits. When it comes to analog, Moore's law has long ceased to exist. Do you know this gentleman, by the way? Andy Bechtolsheim? Yeah, so he was one of the founders of Sun. Now, the younger ones in the audience, they don't know Sun, probably. This was a computer brand. But people my age probably know Sun still. But anyway, so he has a very interesting presentation about this. At the same time, data is exploding. So, what do we do? Well, the problem is there is something called the interconnect problem. It's becoming more and more difficult to interconnect chips, and this is where my company is operating. Okay, so we go back to Shannon again. Now, this is a paper he wrote that is probably the most interesting or most important one about information theory. So you can talk about these channels that the chip-to-chip channels, and you can ask, what's the capacity of these channels? And where are we with respect to capacity? If you talked about wireless, DSL, satellite, magnetic, hard disk, whatever, we are very far. We are maybe at half the capacity or even higher. Here, that's the only odd man out. We are about at 5% the capacity. 5%. We're just so far away from capacity. This is an industry where going from 5% to 10% means shifting of billions of dollars of revenue annually. So why is that nobody is working on this? And that's one of the things I never understood, but I'm happy that nobody else is working on it. So we are now. That's a good thing. But the problem is, of course, it's very difficult here. It's not the same thing that you do in wireless and in other places. Because in wireless and all the other places, there is one component called an ADC, analog to digital converter. It's a component that takes analog signals, real values, and makes from them digital signals. The reason everything works is because you have this ADC, and then you go to the digital world, and you implement all sorts of algorithms you want. Doesn't matter. However, in the chip-to-chip world, this ADC itself, because of the high speed, has so much power that nobody can actually use it. So you have to just get rid of it. Maybe you want to have something, an analog to digital converter, where the analog part is bigger than the digital part. That's perhaps the right thing to do. And that's one of the things we're doing with these Chordal codes. And chord signaling is really, it is an analog to digital converter, right? Because the things we get on the wires is analog. At the end, we have digital. So there is some analog to digital conversion going on here. And this is one where we think the trade-off is good enough so that you can get to the kind of things you want. OK, so if you go back to Moore's paper again, I told you about people talking of Shannon like a prophet. To me, Moore is a bit like a prophet. So I go and read his Bible, which is fortunately only 8 pages as compared to the real one. And there's one paragraph in this where he says, in the entire paper, he's making a case, put more and more and more and more transistors into one component. Integrate, integrate, and integrate. There's one paragraph in which he says, well, there may come a point when you can't integrate anymore. So what do I do then? Then I put special functions on different chips. I disintegrate. And then combine these chips together. And that's exactly what we are doing. So if you look today at the main chip, for example, on this iPhone, it's called a system on chip. It's a chip that has a CPU, but has lots of other components. If you look, for example, at this one doesn't have the Snapdragon. But if you look at one from Qualcomm, for example, it has a modem in there, it has a CPU in there, it has a GPU in there. All these things are in one big monolithic chip. And these things are becoming more and more difficult to build. So what we are advocating is put them on smaller chips and connect these smaller chips inside the same package using one of our chord signaling schemes, which we call Glasswing. Now, every chip is smaller. And so because it's smaller, you have what we call better yield. It's easier to build. And they may not even be in the same process node. And this is a lifeline for Moore's law. This is exactly following this one paragraph of what Moore is suggesting. So the Chordal code we use for this sort of die-to-die connect inside a package is coming from this orthogonal matrix. It transmits 5 wires on 6 bits. And we apply this tempering process. All the stuff I said and bored you with the last hour, we use here. And we have built it. We have built several generations of that. We have built it in a 28 nanometer process. We have built it in a 16 nanometer process. That's a product that we have licensed to one of our customers. Actually, we have licensed it to several customers, but only one of them has allowed us to publicly name them. And that customer is Marvell. You know Marvell? So maybe some of you guys know Marvell because they lost the patent case against one of our colleagues for $750 million. Maybe not. Anyway, so Marvell is building a chip. It's a switch chip, and it's using this technology inside of it. So, we have done a lot of analysis saying how much would this technology save the electronics industry. and it's several billions of dollars a year. And it comes through higher yield, meaning, if you have a big chip, then once it comes out of the fab, it has a higher probability of being broken than a smaller chip. So it's a higher yield. You can, because now you're designing smaller chips, and you can keep them from one generation to the next, the design time is lower, so lower design cost. These chips may not all be in the same very expensive process node. By the way, if you look at 16 nanometer and you have a mask set, today that costs $4 million. 7 nanometer is $12 million. I don't even know what 5 is. I don't even want to know what 5 is. I don't even think that the company, TSMC, would even tell me what 5 the cost is. They know we can't pay for it. So, but then if you go to 28 and higher, the mask set becomes a lot less expensive. So lower manufacturing cost. So this is being considered by many companies in many different spaces: networking, defense, consumer, wireless, etc. Okay.